As we saw in the last video, in the first part of multivariable calculus, which at Foothill College is called Math 1C, we study the forward problem of multivariable differentiation, which looked something like this. We take a gradient operator, we apply it to a multivariable function. In this writing, we're going to assume that we have two variables, but remember, the gradient operator can be applied to any function with more than one variable. And in the forward problem, we are going to calculate, using the techniques of this course, the gradient of this function, the derivative of this multivariable function, which in this case will have two components. It will have the partial derivative of capital F with respect to the first variable x, and the partial derivative of capital F with respect to the second variable y. And these two components, these two partial derivatives, will compose together the derivative of this multivariable function, the gradient. So in this forward problem, we call this thing the gradient operator. In this problem, this was assumed to be given multivariable function, and then the whole idea in this first part of multivariable calculus is this set of partial derivatives are the unknown and desired functions that we are going to calculate. Partial derivative functions. However, before we go on to talk about any of this, I want to really focus on a word that I consider to be a sin, and this is the word given. Have you ever in your life been given a valuable multivariable function and then thought to yourself, oh, I need to find the derivative of this? If you're a normal human being, this doesn't happen. Most mathematicians are never given valuable math. The funny thing about applied math is we have to construct these. So, this study of the forward problem is actually part of a larger process called applied math modeling. And when I say part of a larger process, this is going to be one example of the process of applied math modeling. You'll see other examples in this class and in future math classes. Okay, to talk about applied math modeling, I'd like to show you what this looks like. For those of you watching at home, I highly encourage you to rewrite this diagram in your own writing. Applied math modeling is a four-step process. For valuable applied math modeling, we usually start with a real-world problem. Some problem that exists that we can see, that we want to solve. Perhaps we'll study a problem that's very, very famous in current times, which is I would like a car to drive itself. one of the really interesting things in applied math modeling is when you go from the statement of the problem to an actual meaningful solution, usually this connection can't be made immediately. There's some prohibitive obstacle that makes it impossible to have this happen. So in the case of our having a car drive itself, one is the car can't kill humans. That's a prohibitive obstacle. The next one is this is extremely expensive. To do this well takes a lot of money. So if you go to solve this as an individual, the amount of time and energy that it would take you is prohibitive. You can't do it. So one of the interesting things in applied math modeling is we say, okay, well, we can't go immediately to a meaningful solution. So what we're going to do is we're going to use our scientifically trained mind to transform this real world problem into a set of ideal mathematical models. And the way that this transformation happens actually depends a lot on the classes that you take in science. Every single one of the simplifications to go from the real world problem to an ideal math model is going to be based on your understanding of how the particular components of the problem work, which hopefully is based on scientific study of the components themselves. Once you have an ideal mathematical model, the whole idea in math class is to say, okay, let's take the individual mathematical components of this model, analyze them, use the knowledge that we have from math class, and produce an ideal solution. This ideal solution will not be the solution to the real world problem because it's not the problem that we started with. The ideal solution will be an ideal solution to the mathematical model that came from simplifying the real world problem. At the end of this whole process, we'll do a lot of critical thinking, and this is actually where you would get paid as a mathematical thinker, to make the connection between the ideal solutions that you produced and a meaningful solution to the original problem that you posed. In the case of car analysis or building a drivable car, this actually has a bunch of different problems associated with, one of which is the drive capacity. So if you drive off the center, how do you get it back? Another one is how do you translate data from sensors into meaningful instructions to the car, et cetera, et cetera. Right now, there are a bunch of companies working on ideal solutions to these, and then the meaningful solution will combine those together in a way that keeps drivers safe and a way that's affordable, assuming the whole manufacturing process has been thought about. So, if we think about this class, one of the really interesting things about the problem that we talked about up top is all of the theory of this class is going to assume that you have this ideal mathematical model, that you already have a problem that is in this form. Hey, I have a function that has multiple variables, and I'd like to differentiate that function. So it's here. And then this class will teach you, okay, now that you have that function, let's go ahead and find the partial derivatives of that function, which are the ideal solution to this problem. The really important question that I think we should be thinking about drives the knowledge of this class is where, oh where, do multivariable functions arise in my life, and why would I ever want to take derivatives? Of such functions. And I'm going to put one additional constraint on this. Not only should we know where multivariable functions arise, but I think we should also know, where do valuable multivariable functions arrive? Where do things that you would actually want to spend hours and hours of your life thinking about come up in your life? In the next video, we're going to take a look at an introduction to something called the least squares problem, which is one of the most powerful problems that you'll study in your undergraduate mathematics educations. These problems also give rise to multivariable functions. Are you excited? I'll see you in the next video.